The James Webb Space Telescope reveals that the universe might be twice as old as we previously believe. The evidence is astonishing, and new theories indicate a significant miscalculation in our understanding. Instead of being 13.8 billion years old, the universe could actually be 26.7 billion years old, or even older. Remarkably, the knowledge about the universe's true age has been available all along, but the correct theories were largely overlooked. Since its launch, the James Webb Space Telescope has been making waves in the scientific community. Scientists have been both astonished and excited as long-held theories are being overturned and new revelations are emerging. Through its groundbreaking observations of high-redshift galaxies, the telescope has unveiled insights into the universe's early stages that were once beyond reach. Along the way, researchers have encountered an extraordinary challenge: the discovery of galaxies that are significantly more massive and developed than what our existing models of cosmology and galaxy formation can explain. These observations challenge the widely accepted lambda-CDM model, which explains the universe's expansion. The latest findings strongly suggest that there are significant gaps in our understanding. It appears that our knowledge of the fundamental forces and processes shaping the universe may be far less developed than we previously believed. Science is on the cusp of a paradigm shift, poised for a revolutionary transformation. Amid these groundbreaking discoveries, a new era of physics is unfolding, one that will not only redefine our perspective of the universe, but also reshape the core principles of physics itself. At the center of this new science is the long-ignored work of Swiss astronomer Fritz Zwicky, who proposed a completely new model for the true age of the universe and the phenomenon of the angular expansion of galaxies. To understand the groundbreaking work of people like Fritz Zwicky and these new models, we must first turn to conventional cosmology. Did you know what a feat of astrophysics it was to reconstruct the origin of the universe from numbers and observations? Everything seemed so coherent that these assumptions were long believed to be true. The Big Bang marked the beginning of the universe as we had previously imagined it. This event set the stage for everything that would come afterward, from the smallest particles to the vastest galaxies. In its earliest moments, fundamental elements like hydrogen and helium were formed through processes like nucleosynthesis. The universe then entered a period known as the Dark Ages, spanning several 100 million years during which no light sources existed. Gradually, as the universe continued to cool, the first structures began to form under the influence of gravity. Despite the absence of stars and galaxies, this era was pivotal for the creation of the fundamental building blocks of matter and the cosmic structures we observe today. The era of hydrogen reionization is believed to have started approximately 400 million years after the Big Bang and lasted until around 1 billion years after the event. During this time, the first stars and galaxies are said to have formed, whose intense radiation had enough energy to ionize the neutral hydrogen in the intergalactic medium. This process ended the Dark Ages when the universe became more transparent and light could travel greater distances. However, according to the latest findings, these brightly shining and highly structured galaxies already existed during this epoch. Surprisingly, the analyses of the light revealed that these galaxies do not only contain very large stars of the first generation. The composition points more to a colorful mixture of stars of different ages. These galaxies had already been around for several 100 million years when they emitted this light. Scientists had previously believed that galaxies of this type required more than a few billion years to form. The issue with the previous standard cosmological model is that, based on earlier calculations, the Big Bang was thought to have occurred only a few 100 million years ago at that time. This leads to three possible scenarios. The Big Bang occurred much earlier, making the universe older than 13.8 billion years. Stars and galaxies formed at a much faster rate than previously believed. Or, a third option suggests that the galaxies we observe may have originated from a predecessor universe or one existing alongside ours. Now, let's explore how researchers have previously envisioned the formation of the first galaxies. Galaxy formation supposedly coincided with the beginning of hydrogen reionization and continued as matter in the universe came together under the influence of gravity to form larger and larger structures. These early galaxies are said to have been very small, had high star formation rates that filled the universe with light and energy, and are thought to have contained very different elements compared to today's advanced galaxies. In the previous standard cosmological model, the quasar epoch was a time that peaked around 2 to 3 billion years after the Big Bang. Quasars are incredibly bright centers of galaxies powered by supermassive black holes that consume surrounding matter, exhibit extraordinary energy and brightness, making them the most luminous objects in the early universe. They are believed to have played a crucial role in reionizing and heating the intergalactic medium. But here's the next revelation. Alongside the discovery of impossible galaxies, the James Webb Space Telescope also uncovered 6 likely ancient black holes that existed just a few 100 million years after the Big Bang. This suggests that our understanding of the quasar era's timeline has been misjudged. According to previous considerations, helium reionization took place about 2 to 3 billion years after the Big Bang, following hydrogen reionization. Scientists previously believed this process was triggered by the intense ultraviolet radiation from the accretion of the very first massive stars and quasars. During this period, the previously neutral helium in the universe is said to have been converted into ionized forms, marking a further phase of warming and transparency. The fascinating aspect of this previous model of the universe's development is that it seemed coherent, logical, with few doubts. However, the James Webb Space Telescope has shown scientists, who long believed in this theory, something completely different. The dawn of a new era in physics is becoming increasingly clear. The lambda-CDM model can no longer be considered viable, particularly when it comes to determining the age of the universe. However, some aspects of this cosmic history might still hold truth if the timeline is adjusted. Recent observations and the growing need for new explanations are paving the way for a transformative period in physics, one that will revolutionize our understanding of the universe's history. To begin, let's explore one of the most significant sources of error for astronomers: redshift and the angular expansion phenomenon of galaxies. Astronomers have noticed unexpectedly large angular expansions in galaxies at high redshifts. These observations imply that galaxies could have evolved more quickly and at an earlier stage than what is predicted by the current lambda-CDM cosmological model. To visualize the angular expansion of a galaxy, imagine holding a pencil close to your eyes. It will appear a certain size. As you move the pencil farther away, it seems to shrink, even though its actual size remains the same. This perceived decrease in size is an example of angular dilation, which measures how the apparent size of an object changes based on its distance. The principle works similarly for galaxies in space. A galaxy at a great distance appears smaller than one closer to us, even though both may actually be similar in size. The angular expansion, therefore, gives us an indication of how large a galaxy appears in the sky, not how large it actually is. Now, let's delve into the phenomenon of angular expansion in galaxies and why it holds such significance in astronomy. It is generally expected that as a galaxy moves farther away, its angular size will become smaller and smaller. While this is typically the case, it only holds true up to a certain point. Beyond a particular redshift, a measure of distance based on the stretching of light to longer wavelengths, an unexpected shift occurs. Instead of continuing to shrink, the angular size of galaxies begins to expand once more. This phenomenon suggests that the universe has certain properties in its expansion that do not correspond to our previous models. It could indicate that the expansion of the universe is not uniform and has behaved differently in various epochs. It becomes particularly intriguing if the observed increase in angular expansion occurs at very high redshifts, suggesting that the universe may have expanded differently in the past than our current cosmological models explain. Tired light. Revisiting previous calculations. This is where Swiss astronomer Fritz Zwicky becomes significant. Conducting research during the same period as Georges Lemaitre and Edwin Hubble, Zwicky believed Hubble had made a critical error in his observations of distant galaxies. Born in 1898 in Switzerland, Zwicky carried out research in the USA and elsewhere, gaining recognition for his brilliant yet controversial theories. One of his remarkable ideas is the tired light hypothesis, which he introduced in the 1920s. This concept is now becoming topical again. Zwicky speculated that the redshift of light from distant galaxies might not necessarily be evidence of the universe's expansion. Instead, it could be explained by the loss of energy of light over vast distances. The idea that redshift proves expansion was largely popularized by Edwin Hubble. Although Hubble nearly proved his ideas, there were discrepancies that could now resurface as critical issues. Hubble's findings revealed inconsistent results, while Zwicky's theory, in contrast, provides a clear explanation for phenomena observed in distant galaxies without associated tensions. Although Zwicky can no longer witness the potential breakthrough unfolding today, a contemporary researcher has the opportunity to rise to prominence in the scientific community. The Canadian-based researcher of Indian origin, Rangaram Cherry Gupta, merged Zwicky's tired light model with fluctuating coupling constants. This innovative approach led Gupta to a fascinating re-evaluation of the universe's age. According to Gupta's theory, fundamental constants such as the speed of light, Planck's constant, and the gravitational constant have not remained constant over time but have experienced significant variations. This groundbreaking and dynamic perspective on fundamental constants may offer an explanation for the unusual observations in the angular expansion of galaxies and the inconsistencies in the existing cosmological model. Gupta's research presents an intriguing new outlook. If proven accurate, it suggests that our universe is far more intricate and variable than we once believed. Gupta's revised calculations of the universe's age estimate it to be at least 26.7 billion years old. Subscribe to the channel now and stay updated with all our upcoming videos.